Hello all, welcome to EC Electronics. In this video, we are going to study how to find the modes of operation of a transistor. That is a bipolar junction transistor. How to find the modes of operation we are going to study. Okay, so before going into how to find the modes of operation, let us study the very basics of the modes of operation. That is, what are the modes possible of a transistor, how these modes are achieved, what are the conditions, how to bias the various regions to achieve these modes. Let us see. So even if you know these things, you can find the modes, right? So you should know what are the criteria for various modes. So let us see that first. Okay, so for a BJT or a bipolar junction transistor, there are four basic modes that are, first one is cutoff region or cutoff mode. In this cutoff mode, here I have given emitter base junction and collector base junction. See, EB is emitter base junction, that is this. I have drawn the figure also. This is base, this is emitter, and this junction is called emitter base junction. And there is a collector here, there is a base here. So this is the collector base junction. So we apply some voltage to these junctions and make them as either forward bias or reverse bias. And I have given here what all biasing is given for the two regions for the various modes. Okay, so you should anyway be thorough with this first, then go for the how to find the modes of operation. Okay, so let us see. This is the cutoff region, which is the first mode. There is no order basically. So the first one is cutoff region or cutoff mode. In that cutoff mode, the transistor, here I have drawn the symbol of a NPN transistor. You can also have a PNP transistor. There are two types of BJTs, NPN and PNP. So in this cutoff region, it will act as a off switch. So it has a property of an off switch, which is not conducting mode. So we say when the transistor is in a cutoff region, it is not working, it is not on. Okay, so the both junctions are reverse biased here. That is the emitter base junction, this junction, and the collector base junction is reverse biased. Okay, so in an ideal configuration, we use base as an input, then emitter is grounded. We take output from the collector side. That is a base thing. You can have three configurations: common emitter, common base, and common collector. Here I am just using this configuration where I am giving the input to the base and I am taking the output from the collector. Okay, so when I am taking the output V out from the collector. So we have talked about the cutoff region where emitter base junction, we make it as a reverse bias, and collector base junction also reverse bias. When we say reverse bias, we have to think that these junctions are actually PN junctions. Okay, we just have to make that PN junction as reverse bias. We know how to make the PN junction as reverse bias, right? When we connect, so if this is a PN junction, positive is connected to the positive terminal of the battery and negative is connected to the negative terminal of the battery with sufficient voltage to break this built-in potential or barrier voltage, means that junction is forward biased. If this condition is not satisfied, means it is reverse biased. Okay, just think of a PN junction as emitter base and collector base junctions. Okay, so what we do for a cutoff region, both the junctions are now reverse biased. Okay, next, active region. In the active region or active mode, this is the modes. In the active mode, the transistor acts as an amplifier. Okay, so what is the criteria? Emitter base junction is forward biased and collector base junction is reverse biased. We know that transistors, that is bipolar junction transistors, are current control devices. This should be registered in your mind. BJT means it is a current control device, and in the active mode it works as a current amplifier. Now how this is possible, I'll tell you. Okay, so what I'm going to do is I'm going to apply my input to the base. So there is some current produced in the base. I'm going to call it as IB, which is the base current. Okay, so this IB is actually controlling your output, which is taken from the collector side. We know that there is a relation, that is IC is equal to beta times IB. Now what will happen? Due to this relation, whatever current is present in the IB, it is used to amplify the output current or collector current. So due to this relation, we know when the IB is increasing, your IC is increasing beta times IB. So the current is getting amplified. So that is why in the active region, this condition is satisfied. That is, IC is equal to beta into IB. So when the input current IB is increasing, means the output current IC is also increasing as beta times. So it is actually a multiplication or an amplification is happening. So in the active mode, the transistor works as an amplifier. I hope the concept is clear. Next, moving on to the third stage, which is called the saturation mode. Now what happens here is that, see, this is the relation in active mode, right? IC is equal to beta times IB. What happens when this current IB is going on increasing? We are going to increase the input current IB as high as possible. Now after a particular value of IB, the IC will not get increased anymore. There is something called saturation value, and when the saturation value of IC is reached, then from there it won't increase further. Even if we increase IB, the IC won't increase further. It will get saturated, right? Everything has a saturation point. So likewise, IC also will get saturated, and this state or this mode is called saturation mode, which is a third mode. Saturation mode, what happens? The IC will get saturated. It won't increase further. Even if you increase your input as how many times, even if you increase, it won't increase. So that is called your saturation mode, and in saturation mode, this relationship is not satisfied. These concepts are very easy to study, but you should understand it from a working principle, not just by heart it. Okay. So in saturation, what will happen? The IC will get saturated, or IC sat is achieved. No relation is followed here, like IC is equal to beta IB. It is not followed. Now, what is the biasing here? Both the junctions are forward biased. That is a emitter base junction, and collector base junction is forward biased. Okay. Now, the last mode is reverse active mode. Now, in reverse active mode, the transistor acts as an attenuator. Okay. Attenuator means it is going to suppress the signals. So, what is the configuration here is reverse bias is given for the emitter base junction, and collector base junction is forward bias. That is, this junction I am going to reverse bias. Emitter base junction is reverse biased, and collector base junction is forward biased. Now, when talking about the modes of operation, this reverse active means it is just opposite to the configuration of or mode of biasing of active. We are going to reverse it. The reverse active mode is only possible in theoretical case only, because we know in reverse active mode we are going to make the input side or the emitter base junction as a reverse bias. That means it is not conducting. That junction is not conducting, but the collector base junction is forward bias. We know that transistors are current control devices. If the input region or input current is, we are going to reverse bias, can we get any output value? No. So it is not possible to work properly in the reverse active mode. So it is not practically possible, because we know it is a current control device. That is, only if we apply some input to the that is input current, only then we can get some output values. So if we are going to make the emitter base region as reverse bias and collector base junction as forward bias, means that is not practically possible. Okay, so this is only possible for just theoretical case, reverse active. So all these three modes are possible practically. Okay, so in the cutoff region means the transistor is off, and in active region means this relation is satisfied, and this saturation region means it acts as a on switch, or this relation is not satisfied and it reaches the saturation value. Now let us think, or let us talk about what are the conditions to find whether the transistor is in cutoff region, active region or saturation region. Okay, so let us see the most important part of this video, that is how to find whether the transistor is in cutoff region, active region or saturation region. As I told, we are not generally considering the reverse active region because it is not practically possible. Okay, so mainly or 90% the questions will be from either active or saturation region. And you have to find whether the transistor is in active region or saturation region. That is the case. Now, let us see the conditions for the active region first. Okay, active mode means what? Active means, I'm going to write the conditions again. This region, that is base emitter region, is forward biased and the collector base region is reverse biased. So keep this thing in mind. Okay. Now, what is the condition to achieve this? One important thing to note is that, so this is, I'm using here a silicon transistor. I'm just considering that this transistor is a silicon type of transistor. And this region is called base emitter region, right? So, for the base emitter region to get forward biased, what is the voltage required? Just think of a silicon PN junction diode. What is the cut-in voltage here? It is 0.7 volt, right? Also, this positive is connected to the positive terminal of the battery, negative is connected to the negative terminal of the battery. Now, consider this figure. I've just drawn a figure to represent a transistor. Here, I'm going to give input to the base region. So, Vin is applied to the base and emitter is grounded. So, it is positive and negative. Connection is correct. Now, if the voltage coming across this junction, that is VBE, base emitter junction, is equal to 0.7 volt, then this region is forward bias. Okay, so base emitter voltage should be equal to or greater than 0.7. Only then the base emitter junction will get forward biased. So that is one condition, that is VBE should be equal to or greater than 0.7. Ideally we get 0.7 only. So VB should be greater than or equal to 0.7 to turn on the base emitter PN junction. I hope it is clear. Next, we need to make this junction, that is VCE, as what bias? Reverse bias, right? So, if you look at the collector side, I am using a NPN transistor. So, for a NPN transistor, we need to make N as what bias? N should be, that is here, there is a PN junction diode. In order to make it as a reverse bias, we need to connect the negative to the positive terminal of the battery and the positive to the negative terminal of the battery. So, rather than just thinking positive and negative, we can think this has a higher voltage and this has a lower voltage. Okay. So, the negative should be connected to a higher voltage and the positive should be connected to a lower voltage to make it as reverse bias. Okay. So, here in order to make the collector base junction as reverse bias, we need VC should be greater than VB. Okay, so this is the condition. We take VC, that is collector region, collector voltage, as greater than VB. Okay, so that is the case for a active region. So if the transistor is working in active region, these conditions should be satisfied. Another condition, one more condition is there. I'll explain it while explaining the saturation mode. Okay, so this is the case for a active mode. We normally use these two conditions. VB, that is a base emitter region, should have a voltage or potential of 0.7 and VC voltage, collector voltage, should be greater than VB. So here this junction, if you consider, the negative is connected to a higher potential and the positive is connected to a lower potential to make it as reverse bias. I hope it is clear. So this is a condition for a BJT to work in an active mode. Next, let us go to saturation mode. Okay. Now I'm going to talk about saturation mode. Here again, what are the conditions? The emitter base junction or the base emitter junction is what bias? Forward bias. Here the junction is forward bias, and here also it is forward bias. So two forward bias we need. Keep that thing in mind. Let us see for the conditions. Okay, in saturation mode, we are again going to consider the base emitter region as forward bias. So what is the voltage required? VB should be greater than or equal to 0.7 volt. Okay. Next, here as I told earlier, we are going to make this again as what bias? Forward bias. So I'm going to make it again as negative connected to lower potential, positive connected to higher potential. So what will be the case here? Here the case is VC is less than VB or less than or equal to VC. Ideally we can write VC is less than VB. So while doing the problems, as I have done some problems, I have obtained in saturation mode mostly the voltage VC will be obtaining as negative. So if you are obtaining VC as negative, you can think it might be saturation mode mostly. So this is the case. Okay. Next, we have told that in the saturation mode, what will happen? As we increase IB, this relationship IC is equal to beta IB is not satisfied. That is, even if we increase IB, IC won't increase. It will get saturated. So that is the case. So what will happen to the V out? So here V out equation is V out is equal to VCC, that is this voltage, minus the voltage drop across this resistance. That is, what is the voltage drop across this resistance? The current flowing through is IC. IC into RC will be the voltage VC, or we take it as V out. Okay, so what will happen in the saturation mode is that when the value of IB is increased and after the particular saturation voltage, the IC will get saturated. Okay, so we will get V out is equal to VCC minus IC sat into RC. Okay, so this voltage will be almost equal to 0.2. Okay, so the voltage will get dropped due to the increase in IC. The IC will increase from the active mode to the saturation mode. We are increasing the IB, and as a result, IC will also increase and reach its maximum or saturation value called IC sat. So the value V out will get reduced, right? So V out will be equal to 0.2 volt. Okay, so we can consider this V out as the potential difference between these two regions, because this emitter region is grounded. So we can think V out as VCE also. So the value of VCE will be equal to 0.2 volt in the saturation mode. That is, the voltage will get reduced, you have to think. So that is another criteria in the saturation mode. That is, if that is a third criteria. VCE is less than or equal to 0.2 volt, then it is the saturation mode. And I've told you that active condition has one more criteria. I'll explain in saturation, right? So that is this one. So in the active mode, what is the case? So for active mode, VCE should be greater than 0.2 volt. Okay. That is what is happening here is, as I told, we are taking the output from the collector side due to the increase of IC, and IC is reaching the saturation region or saturation value. Value of your V out or VCE will get reduced, and this value will reach 0.2 or less than 0.2 for the saturation mode. So if the value is greater than VC is greater than 0.2, means it is in the active region, or the collector current has not yet reached its saturation state or value. So this is another case. You have to put it in the active region. That is, Vc is greater than 0.2 means it is in active. And Vc is less than or equal to 0.2 volt means it is in saturation region or saturation mode. So these are the three conditions for saturation. So in cutoff mode, what is happening? Here, this region is reverse bias and this region is also reverse bias. So we have to club both the conditions. That is, here VBE is not equal to 0.7. That is, not equal to means it is less than 0.7 volt. And here this region is also reverse bias. That is, VC is greater than VB. Okay. So this is the two conditions for cutoff region. As I said earlier, in 90% of the questions, they will be asking for the saturation region and active region question. That is, from these two regions, you need to find whether the transistor is in the saturation region or active region. Now, let us do some problems for finding the modes of operation of the transistor. Okay. Now, we are going to do the problems for finding the modes of operation of a transistor, of transistors. Okay. So, let us see. So, there is a circuit given, and this circuit is having two resistors. One is connected at the base, one at the emitter. There is an input given to the base, which is a 2 volt. Okay, so what we do here is we are going to assume that the transistor is working in active region. So we have set certain conditions for active region, and there we have considered that the transistor has to get a voltage of 0.7 across the base emitter for getting it in active mode. That is, for making the emitter base junction as forward bias, and we have found, or we have made the condition that Vc should be greater than Vb for collector base to get reverse bias, right? Now, in order to find whether the transistor is in active mode or saturation mode or whatever mode, first we are going to assume that the transistor is in active mode. Now, why we are going to assume, I'll tell you. Okay, so this is a standard procedure we do for mostly all the questions. That is, first we are going to assume the transistor is in active mode. Okay, and then we are going to check whether the active mode is satisfied or not. Okay, if we found it wrong, we'll correct the mode as wise. So here we are going to assume that the transistor is in active mode. So what was the condition for active mode? Here the base emitter region should be forward bias and the voltage VBE should be equal to 0.7. Okay, so the base emitter voltage should come as 0.7 for the base emitter region to get forward bias, right? So that is one condition for active mode. So here we are assume active mode. So do this for all the problems. First assume it is in active mode, then check for that. So now there is a resistor of 1 kilo ohm connected to the base, and the current flowing through it is, I am taken as IB. Current is IB since it is a base terminal. Now I am going to apply Cutoff voltage law, that is KVL, for this particular region or this particular loop, say. Now what is the Cutoff voltage law? So here there is a voltage of 2 volts. So minus 2 plus, there is a resistor and current flowing through is IB. So plus IB into 1K plus, here there is a voltage drop, right, which is 0.7. Since we have assumed it is an active region, we have taken the base emitter voltage is 0.7. That is the minimum voltage required to turn on the PN junction in the base emitter region. So plus 0.7 is equal to 0. So this is KVL. Okay. So minus 2 plus 0.7 is 1.3, right? That is 1.3 is equal to IB into 1K. Sorry, this is 1K. Now IB is equal to 1.3 milliampere will be your value for IB. Fine. So we have obtained the value of the base current as 1.3 milliampere. Now what will be the voltage coming? So since IB is 1.3 milliampere, what is the voltage drop across this resistance? It is 1.3 milliampere into 1K, right? So it is a 1.3 into milli into 1K means 1.3 volt. Okay, so we got VB is equal to 1.3, we got the voltage drop across this resistor is equal to 1.3 volt. So what we have done, I will tell once again. See, in order to find the actual mode, first we are assuming the transistor is in active mode. And we are assuming that the base emitter voltage has to be minimum 0.7. So we take it as 0.7. 0.7 we have taken as base emitter voltage. And we are going to apply a KVL in this region. So it is a -2 plus the voltage drop across this plus the base emitter voltage is equal to 0. And from that we have obtained the IB or the base current as 1.3 milliampere. So if we have IB, we can find the voltage drop across this resistor, and that we have obtained as 1.3 volt. Okay. Now, if there is a total 2 volt and there is a 1.3 coming across this resistor, means the remaining will be coming across the base, right? So as I explained in the beginning, if there is a series resistor and a base, the voltage drop across this resistor -2 volt will be the voltage coming here. So how much it is? 2 minus 1.3 volt is equal to 0.7 volt. That is, there is a 0.7 volt coming across the base. I hope it is clear. So there is a 0.7 coming across base, and we know that emitter is grounded. So what is the voltage difference between base and emitter? It is 0.7 only. Base is having 0.7, emitter is grounded, means difference in potential or voltages between that terminal or that region is 0.7. So that is equal to VBE, right? So VBE is again obtained as 0.7. That is, our assumption is correct. Okay, next. So we have obtained that. What we have obtained here? Here we have obtained that the BB is 0.7. Next we have to check for the collector base configuration, whether it is forward bias or reverse bias. Now we are getting that the base emitter region is forward bias. Okay. Now we need to check whether the collector base region is forward bias or reverse bias. Okay. Now we have the value of IB is equal to 1.3 milliampere. Now we have assumed, see here, we have assumed it is an active region. So what is the relation between IC and IB? IC equal to beta times IB. So IC will be equal to, beta is 100 into 1.3 milliampere, which is equal to 130 milliampere. Fine. Okay. Now we have IC value. Now we need to find what VC to compare whether it is VC is greater than VB or VC is less than VB. We need to find. Okay. So VC means the voltage across or voltage coming to the collector region. So this is VC. So I have explained earlier also what is VC or V out. VC is equal to VCC minus IC into RC. Okay. So what is VCC? It is 10 minus IC is 130 into RC is 2K. So 10 minus, so this 130 is milliampere. Okay. Milliampere into 2K. Okay. 10 minus milliampere and 2K will get cancelled. 10 minus 130 into 2 is 260. So 10 minus 260 is minus 250 volt. Okay, so it is a minus 250 volt. Now we have obtained VB is equal to 0.7. Now we have VC is equal to minus 250 volt. Now we need to check for this relation. Okay, so here one thing is very much clear. VC is very less as compared to VB. So VC is less than VB. Right. So now when VC is less than VB means the collector base junction is what bias? It is a forward bias, because in order to make the collector base junction as a reverse bias, we need VC should be greater than VB, not VC is less than VB. So the condition is not satisfied for active region. So it is a what region? This is a saturation region. Okay. Now, how we got it as saturation region? Because we obtained that the collector base junction is also forward bias. This is also forward bias, means it is a saturation region. Now, this is how you need to find the modes of operation of a transistor. So now we have the collector base junction forward bias and also emitter base junction is forward bias. So this is how we have to find whether the region is active or saturation. So generally we do like this. We assume whether the transistor is an active region, then we check for the condition whether it is satisfied, whether our assumption is right or not. Okay, so this is how you have to attempt the questions for modes of operation of a transistor. I hope the concept is clear to you. I hope the conditions, how the conditions is coming, what are the conditions is clear to you now. So this is all about this video. We'll be doing part 2 of this if you want more problems. Okay, I hope anyway the concept of modes of operation and how to find is clear. We generally do it by assuming, and we check for whether the assumption is correct or not by verifying the conditions. Okay. So if this video was useful for your preparation, please do give it a thumbs up and also share this video with all your friends. And if you want more videos, please do subscribe to the channel. Thank you and keep on watching.